Welcome to Formulation Simplified, Finding the Sweet Spot via Design and Analysis of Experiments with Mixtures. I'm your presenter, Mark Anderson, with Staddies Incorporated in Minneapolis. Thanks for joining me today as I talk about mixture design and how it can help you do multi-component testing on your formulations that will lead to sweet spots where all product specifications are met. To make the most of this opportunity, I'd appreciate if you'd hold off on questions till afterwards and then email them to me, Mark, at staddies.com immediately afterward. That'll prevent audio disruptions and help me, present as much material as possible. Thank you again for attending. Let's begin. To begin with, I would like to point out that we have a new reference coming out called Formulation Simplified in 2018 from Taylor and Francis under their CRC imprint from Productivity Press publishers in New York City. This will round out a trio that began with DOE Simplified, first published in 1999, now in third edition, that covers the basics of process screening and characterization, mainly two-level factorial designs, and then moved on to the next level, which is Response Surface Methods, or RSM, simplified for process optimization. That now is in second edition. And then finally now we'll cover the situation for formulators where they need to work within these triangular spaces and do special types of designs that are called mixture design. We have a primer that incorporates the first three chapters of this. That's posted on the web. It's free, and you can find that at the 3w.staddies.com at this location. But if you just go to the main website and look for the link that says I'm a formulator, then you should find that. So look for I'm a formulator, and I'm just going to write out I'm a formulator on the main web page, and you'll be able to find a path to this primer. It's going to be a good adjunct to this presentation. So this is me at the left. In the middle is my business partner, Pat, who is our founding principal and the co-author of the first two books. And then to the right is our PhD statistician, Martin, who's the co-author for the Formulation Simplified. So the three of us will be the ones that are putting together this new book. So those will provide some good backgrounds for those of you that are just getting started. They're readily available off of Amazon. They also come in ebook format. So let's talk about the what's in it for me, or the WIFM, for this webinar. First and foremost is I really want to start by just introducing these tools for multi-component product development and optimization. How do they work? What are the advantages of doing this versus the old-fashioned one component at a time approach? And then we'll get really into the tailored tools that can hone in on the actual sweet spots for these recipes, and also then thirdly provide several real-world examples that will give you some inspiration on taking hold of these tools. So let's see how Staddies makes formulation optimization easy for its users. Now, just to make sure you're with me, if you would please press that raise hand button on your control panel. Tyler, I see. Who else can find that hand? Tian. I'm getting a good sampling. Stephanie, Shelley, and so forth. Okay, so it looks like I've got plenty for our sample size that tells me that my audio and video is working. Thank you for that feedback. What I'll do from time to time is come back and ask you again to raise your hands so that I'm not going offline unknowingly and just blathering on. So let's begin with what is really mixture design all about. This was pioneered in the 1950s by Henri Chaffee at UCal Berkeley, and it became kind of the final part of our trio of tools, starting with design of experiments itself, invented by Ronald Fisher, and the analysis of variance, the F-test, simple comparative experiments, the two-level factorial designs and general factorials. All those were developed in the 20s and 30s. Then in 1951, George Box invented response surface methods while working at Imperial Chemical. And then finally, Chaffee came along and basically adapted responsiveness methods to this mixture situation. So the considerations are that they're not factors, but rather ingredients, or we'll call them components in a mixture. And so what we'll do is we'll try to use two different sets of language, a la John Cornell, who really popularized these techniques. When he presented at a presentation years ago, I was reminded that I shouldn't be calling these factors anymore, but rather ingredients or components to kind of separate out the special treatment that we need to apply. So that's the terminology we'll use for this type of design of experiments that's applied to mixtures. Then what's more important is that the response is a function of the proportions and not the amounts. So a prime example would be foods and beverages, such as this nice milkshake that this lovely young lady is sipping, is going to be tasty because it's got a good amount of sugar, it's got a good amount of milk fat, and of course, the chocolate. So by getting the right proportions of all these ingredients, we'll have a very happy young lady when they taste this. The amount of the milkshake is a bit excessive. I don't know if she's going to make it all the way through, but she takes one little taste, and like Shakespeare said, you don't have to eat the entire ox to know that the meat is tough. Okay, so a little taste will do, and she knows that this is going to be delicious. So those are the two considerations. And then finally, given these two conditions, if we fix the total, which is an equality constraint, and this total could be 1 glass, for example, or 100 weight percent, it will facilitate the modeling of the response as a function of the component proportions. Now, what I've found over the years in using these tools, teaching these tools, is that when we get people started on the two-level factorial designs in particular, they get really excited and they suffer from what's called the new hammer syndrome, where everything looks like a nail. So naturally, when they come across a mixture, having learned about factorial design, they try to apply a two-level factorial. And let's see how that fails in this example of lemonade. So we have an entrepreneur that is going to set up a stand, and they decide first they better experiment with how many lemons they put in, and they go from 1 lemon at the low level to 2 lemons at the high level. And then also how many glasses of sugar water that they put these lemons into, and we have 1 glass of water at the low end and 2 glasses of water at the high end. Now this forms a design that mathematically would be expressed as 2 to the power of 2, which of course, if you work out the math, is 4 runs or 4 combinations. Now already as you're looking at this, you may be realizing that if we just take a little sip out of each one of these, there's actually not 4 different combinations here. But of course, when we go 1 lemon to 1 glass of water, and we go 2 lemons to 2 glasses of water, it's really just a scale up of the recipe. And so therefore, this is not a very efficient experiment. Do you see that? If you see that and you agree that this probably isn't a very good experiment, press that raise hand button. Hey, Raymond, Ray, I'm in the R's now. We've got a pretty good audience here. Let's see, let's go at the other end. Abraham is at the top, and we've got Chin at the bottom. So thank you, everybody, for giving me that feedback. It's good to know that you're with me so far. So let's continue on then and think about how this lemonade experiment might be done more efficiently. And here it is. So what we've done is we've put together these 2 factors into one input variable, which is totally correlated between the 2 components of it, so that as the lemons go down, then directly the water has to go up to fill out the glass, right? And vice versa. Now, an experiment that we would run on this would be try doing pure lemons. And then we would do some kind of a sensory measurement, let's say from 1 to 9 for the taste. And 9 is our aim, which is heavenly nirvana. And 1 is where we want to avoid having Mr. Yuck, spit it out, horrible. And then 5 is kind of, sort of in between. So in this hypothetical experiment, I think it would be good to assume that if we use all lemons, it's going to be pretty sour, and maybe we might get a value of 3, if even that. Now, turning our attention at the other end of the scale would be the pure sugar water. And these are actually coded from 0 to 1, and that's what we use for the mathematical modeling. But you could also consider this to be 100%, of course, at the right-hand side for the sugar water. Now, sugar water is very tasty, and I think we might want to come up with something like a 7 on the taste of the pure sugar water. But then, of course, we would like to try lemons plus water and see if we can make something even better. And so we might do a 50-50 blend. And then these would be 2 check blends that are between the overall centroid and the extreme vertices, okay? So now we have 1, 2, 3, 4, 5 different levels. Maybe we would replicate, the ends and replicate the middle, and we make a nice little experiment. So then we're going to fit the data, and lo and behold, we find that we get this response surface curve that is deflected upwards, and this means that we have a synergism where the 2 ingredients together are better than either one alone, which is super duper, and exactly what we're hoping for. Now the model here is known as a Chaffee polynomial after the inventor, or sometimes I just call it a mixture model to make it simpler, okay? Now what's different about this mixture model is it has no intercept, but it turns out that Chaffee needed to use a normal quadratic model and then account for the total constraint, and he came up with this adaptation for mixtures that accounts for that total constraint. And it actually works pretty well, and we would consider this to be a nonlinear blending equation. So you could also term it a quadratic or second order equation, but let's think of it as a nonlinear blending situation because of this second order term here. Before we get to the second order term, let's think about the first order terms. And actually it's quite easy to fit because beta 1 is just 3, which is the value we get with the pure x1, and beta 2 is just 7, which is what we get on average for the pure sugar water. And then beta 1, 2 would be 4 times this deflection times 0.5 times 0.5, which would be 1/4. And so that would capture this deflection above the linear blend line, which is a straight line. And of course, the actual peak of this is going to be a little bit to the right of the 50-50 because of the tilt in this towards the sugar water. So if we did a numeric optimization, we might find that something like this would be good with just a little bit of lemons and mostly sugar water, and maybe we would get not quite to the 9 heavenly nirvana, but maybe we get up to 8 or so on the sensory scale. So does that look pretty tasty to you, the actual concoction of the lemonade and also this tool that we're using? Does it look enticing? If so, press that raise hand button. Okay, and Tom is quickest on the trigger, and the others are coming through very nicely. So thank you for that that backup on my story. So let's move on now that we've got this introduction done that tells us that, hey, this factorial design really shouldn't be applied to these mixtures. Let's account for the fact we have our total and recognize that if we have Q ingredients, we really only have Q minus 1 variables to experiment on, because once we know Q minus 1, the last component is fixed. And so that's one of the aspects of this that we have to contend with. We also have to realize that a different type of model has to be used than maybe what we're used to with factorials and response surface methods. So let's continue on to a more interesting situation with 3 components. Now, I've actually come across the new hammer syndrome. I was working with a company here in the Twin Cities. It happens to be Cargill, which is a very, very large, probably the largest privately owned corporation in the United States, which is down the street from where Staddy's is located. And I was working with a lady that was feeding these ruminants different nutrients, and she learned about 2-level design and how you can do 2 levels with 3 factors and form this little cube here. And basically what she had was 3 ingredients that she wanted to consider, but she wanted each of them to go from 0 to 100%. And you probably can anticipate what's going to happen here. Well, if you put all zeros in, which is at this origin, the total is 0%, and the ruminant, which is a cow, will die. So that's not good. And on the other side of it is if you try to put in 300%, that's too much of a good thing, and you'll kill the cow. The cow will die. And even the 200% will not work. So straight away, we need to shift over our thinking to this mixture space. And here what we have is the 100% corner for A, the 100% of B, and 100% of C are the corners of this simplex, which is an equilateral triangle. And these are called pure blends, which is a bit of an oxymoron because they're really pure, they're not a blend, but that's what they call them, pure blends. Then along the midpoints of the edges, like halfway between A and B, are what are called binary blends. So those are the midpoints of the edges. And then in the middle is something called a complete blend, which has some of all the ingredients in it. And at the very middle is the centroid. And so we're going to use the term centroid instead of the word center point, which you normally would use for the process space. So you can see where there's a little difference in the terminology that helps us separate out these 2 methodologies between the process screening, characterization, and optimization, and the mixture design optimization. Now, I came across this triangle graph early on in my college education at University of Minnesota. I'm a chemical engineer, and the department is combined with material science. So in material science, as I'll show you in just a minute on the stainless steel case, the phase diagram, as they call them, is very useful for formulating metals. Now, if you went to the cabinet and tried to get a piece of paper with the right coordinates on it, you would look for something called ternary graph paper. And I always thought of this as ternary, T-U-R-N-ary, because when you look at this graph paper, you have to contend with the fact that it's going in 3 different directions. To start with, we can look at it straight up from 0 to 100% at the opposing apex, and that would be ingredient X1 or A. But now we have to turn our attention to this side of the triangle at 0 of X2, which is B, and then we can see the rulings coming out here, 10, 20, 30, etc., going in that direction. And then finally, we turn it one more time to this left side, which is a 0 of X3, which is C, and then we see the rulings coming out on that. But what's really, really cool is that once you know any 2 ingredients, let's say 60% of X1 and 20% of X2, then the third will fill in to get to the total, which I'm just going to say is 100 rather than 1. So for example, in this case, at 60, I'm going to go from the bottom and I'm going to go up till I get to the 60% line and cut across on that, and that'll be the 60 of A. Then I'm going to turn my attention to the right side and I'm going to look for this direction going 10, 20%, and there's actually another line here, which is the 20% of X2. And now, without actually knowing what X3 is, I can read it off the graph because I'm going to go from the left side and I'm going to read off 10, 20%, and hopefully that adds up to 100 if I did my math right. So that's pretty cool, I think. And then in the material science class, they brought up this diagram, which is pretty scary looking. But it turns out that if we go right to this point here of the composition of chromium, nickel, and iron, we can make a really good stainless steel called 18-8 stainless steel that's good for kitchen flatware. So how does that work? Well, if we go from the bottom to the top, we're going in the chromium direction, and it turns out we're going 18% up on the chromium. So that's where the 18 comes from. then the 8 is actually going from the left side to the right side, which is a nickel, and it's going just a little ways from the left side in. In fact, it's going just 8% in on the nickel. Then, of course, the last part of it is a major component, which is the iron, and that's coming from the right side all the way over almost to the corner. And so then we could do the math on 18 and 8, and let's see, that's 26. Then I think it's 74 if I'm doing my math right, up to 100%. So this is the way that this ternary or phase diagram works. Does that make sense to you all? Press your raise hand button if you're still with me. Okay, and Tom, I'm kind of in the middle of the alphabet here. There's a James, Aaron, Austin, etc. Okay, thank you guys and ladies for attending this presentation and staying with me on this. Okay, so now we're going to move on to an example, and this one is a solid rocket fuel. Now, what they're trying to do is get the elasticity of the fuel as high as they can, so that we don't get another space shuttle disaster. Luckily, they're not shooting off that space shuttle anymore, but if they ever get around again, hopefully they'll have a more elastic solid rocket fuel for these new rockets that are coming in. So what they did is they looked at total fuel of A, 100%, B at 100%, and C, and these red dots represent actual experiments where they measure the elasticity at these pure blends. And each one is done twice, so it's a replicated experiment, and it would be done in a totally randomized blend order, of course, so that any lurking variables are not biasing our estimates. And then we would think about doing combinations of things like A and B. This would be a binary blend, and it turns out in this case that there's really no chemistry, let's say, between A and B. It's flat on this corner, on this side. So this is what we call a linear blending situation. But when we look at the combination of C and B, that really shoots up in terms of the elasticity. So here we have a synergism where two things come together and give you more than either one alone. Now keep in mind that things are not always going to be good. Sometimes it'll go negative, and that's where you have an antagonism between two ingredients. And that antagonism, I can give you an example of where I've got two girls that when they were young, either one alone was delightful, but together they were terrible, vying for my attention. And two boys, and the same thing happened with them, only worse. There was antagonism. And then now I've got 5 grandchildren, and the pattern has repeated. I've got 2 boys and then 3 girl grandchildren. So now I'm taking care of them, and I see the same phenomena of antagonism at a certain age. But then, luckily, when they get old enough, there's synergism because it's actually easier to take care of the 2 of them when they get older than either one alone because they play with each other. So think about that. That's kind of a neat little example of antagonism and synergism. Okay, so in this case, we can actually take this data and we can do a least square regression to a model that Chaffee developed. And this model has got an extra part to it, which is third order. And this is called a special cubic term. And this gets us the bulge in the middle. So this is a good model to consider, and you might even design an experiment, particularly with only 3 components, so that it would have enough unique levels to be able to fit that special cubic term, just in case there might be a 3-way chemistry going. Now at this point, things get a little bit dry with the presentation. So I always bring up this Far Side cartoon because I think it's pretty funny. And what it is there's always a joker in the lab. And just when you're putting the final nail into the nose cone, they sneak up and they blow up this bag just to keep you on your toes. So hopefully you don't have a person like that in your lab. I actually have had people that do that sort of thing, and it's pretty nerve-wracking. So I recommend if you have a trickster in your lab, you might want to transfer them over to a different department. So now let's turn our attention to another case study, and this is one that's written up as a tutorial for our software that you can work through. And what I'm going to do is I'm going to demonstrate a new version of software, version 11, that we are really excited about. It's primarily an interface enhancement that also will take us into other platforms that will extend our reach. And you'll see more about this later as we get closer to the release of it. But I thought I would give you a sneak preview of version 11. And in this particular case, there's a detergent chemist. They actually want to do water from 3% to 8%, but we'll see that that 8% isn't going to work, because if they also want to get at least 2% of alcohol and at least 2% of urea, and then furthermore keep the total at 9%, then obviously this 8% can't work. So I'm going to go ahead and enter in 8%, and then you'll see how that gets caught by the program so that you don't try to press ahead with an impossible combination. So I'm going to move over now to the program, and this is Design Expert version 11. Then I'm going to open up a file, and we'll start working with this detergent case, and I'll rebuild it so that you can see, how it actually would be done using the tool. So let me open that up, and then I'm going to use the control mouse wheel to make this font a little bit bigger and see if I can get it where you can read it. Okay, now I would ask you to raise your hand again if you can see on your screen these ingredients of water, alcohol, urea, and then the responsive viscosity, etc. Okay, so it looks like we're getting some success here in terms of our internet connection. Isn't that wonderful? So thank you for letting me know that you can see this. Now what I would do is I would eyeball this data, and it turns out, just FYI, that first and foremost is we don't want this to be too cloudy. And actually, once it goes above 900, it's going to be too cloudy, and the detergent will be rejected. So that tells you something about the chance of this working. But even worse is the viscosity has to be between 39 and 48, and there's actually only some results that come in that range. And then do we have any that fall in the range that are also low in turbidity? Yes. So this tells us there might be a sweet spot. And so that's going to be our mission, is to see if this holds up, if it's significant, and whether we can discover a combination that will meet these requirements. Then last but not least is the cost. And in this case, and it works very nicely with mixture design because you've got all the units of measure the same for your inputs, you can put in an equation very easily with our program. And this equation actually is a function. You won't be able to see it too easily, but the water is essentially free, but then there's a cost associated with the alcohol and urea. And so we've actually gone ahead and just typed that in. And what I'll do is I will show you first the cost, because that's already determined. So this is a contour graph, which isn't very useful for this view of cost. Maybe the 3D surface is a little bit better. You can see the linear cost function, but probably the best thing here would be to do a trace plot, which starts at the overall centroid and then holding all the other ingredients in constant proportion, just as one ingredient at a time. And now you can see very quickly that as the amount of water increases, the cost of the formulation goes down. And the most expensive ingredient is B. The more of that we put in, the more expensive it gets in dollars per kilogram. Okay, so we knocked that one off right away. Now let's turn our attention to the viscosity response. And what I'm going to do is just kind of press through this very quickly because of the time is so short. However, let me say that the program is very thorough in starting off and looking at what's going to happen as you add the linear blending terms above and beyond just the mean, and tells you whether there's a significance to that. And then it adds further the second order terms, which are called quadratic, which are the non-linear blending terms. And you get even more significance to that on top of the linear. But when you put in the special cubic, which can be estimated, there's no significant improvement. And I can make this even a little bit bigger, I think. Yes, if I press the scroll mouse wheel. Okay, now I'm making it really big. And you can see where this would be a good place to draw the line. And that's what's suggested by the program, by its scoring system. But also you might be looking at these adjusted and predicted R-squareds. And these are, the best of all the different models. And never mind the cubic and these other higher order quartics, etc., because we don't have enough unique blends to fit all the terms in the model. Those are aliased. So it looks like quadratic is going to work. So now the program has pre-selected the quadratic. Now what I'm going to do is look at the entire model. However, there are auto-select methods available such as AICC forward, but p-value backward is maybe one that you're more familiar with that can reduce this, but I'm going to go ahead because there's not that many terms and just fit the whole model. So here is the analysis of variance, and you can see that the overall model is significant, and then we see that 2 of the second order nonlinear blending terms are significant. This one term that's AB could be taken out of the model, but it would make no difference. So I'm just going to leave it. And also we have an insignificant lack of fit, which is good. So these are all features of the program. You can see that we have these multi-views now available with version 11. That's going to be really handy. Then similarly, even better yet for the multi-views are the diagnostics, where you can see all at once the key diagnostics. And in this case, there's nothing abnormal, no outliers, no need to do a transformation, and so forth and so on. So I can look at this very quickly and see that this is probably going to work. And so now we're going to turn our attention to the actual graph, the contour graph, and we actually want to be somewhere between 39 and 48. So we could try to set contour values at these different levels that are within our specification. So 39 is one level, and the other level is 48, which must be in here someplace if I want to add a contour and then set the contour value exactly to 48. Now I can get an idea of what the region is where we can meet the viscosity specification, and I could begin setting some flags. For example, at this overall centroid, we get viscosity that's pretty good. It's between the two levels that we want. However, and we'll take a look at this in 3D view. However, we also have to contend with the turbidity. So let's look at the turbidity, because that's going to perhaps close us off. And we go through the same process of fitting this, and it turns out in this case that the special cubic actually does give us a significant improvement. And so then we model using that extra term for the turbidity, check the ANOVA. Again, there's a couple of terms that we probably could throw out, but it makes no difference, so I'm not going to bother. The lack of fit is insignificant. The diagnostics are good. And now we see something that's kind of like the rocket graph that's got this big increase in the middle. What the thing is, we don't want that. We don't want that middle part, because that's got turbidities that are very high and it'll be rejected. So we really want the parts around the outside of this. Now, the problem is that it's going to block out the good viscosities. So somehow we got to deal with this trade-off, and that's going to come into play with the numeric optimization. Here we can dial in, putting the input variables at their ranges, what viscosity we want, the target of 43, the range of 39 to 48, and we form this desirability tent that we want to get underneath. If we're outside of it, it's got no desirability. And then turbidity is actually a minimization goal. But once we get below 800, it's essentially clear to the naked eye. So we don't really need to worry about getting any lower than that. So we want to be realistic on setting these threshold limits. And then finally, cost, of course, should be minimized. And we could give these different importance levels if we want. Right now, I've got them all at the same importance level. So let's see what the computer comes up with for the solution. Aha. So it's telling us that if we go pretty high on the water, and relatively low on the alcohol and urea, we can hit our viscosity dead on and get a very clear solution at a very minimal cost. All right, now I've just gone through quite a lot all at once, but would you like to see a solution like that? If so, raise your hand. Okay, so you're agreeing with me. Either that or you're just trying to humor me by raising your hand. But hopefully you agree that this is a very nice outcome. Thank you for that. So then one more thing, and there's actually a couple things, but one more thing as far as the optimization would be to just look at it very simply as a graphical overlay where we just put the spec limits in on the viscosity, just the upper spec on turbidity, and then set some kind of a cost goal like $2 per kilogram. And then this gives you a nice visual of where the sweet spot is. And actually, this is a pretty good sweet spot in this corner, this part over here, but there's also some sweet spots over here in this part. But in the middle, it's too high in turbidity, and on the outsides of this is too high or too low in viscosity. But only in these yellow zones are you going to meet both the turbidity and the viscosity. Now, if the manager comes in and starts putting pressure on the cost and says, I want it less than $2, what's going to happen to our window? It's going to start closing out, right? And eventually what will happen if the manager takes over and keeps pressing the cost down is that one of these windows will close out, and of course you're going to favor the formulation that has more water. Do you see that? So this actually can be a nice little what if graph, because you can move these different limits around depending on what the customer and the manager wants. And you also, of course, can change in the numeric criterion, what the different relative importances are, what these specifications really are. All of that is subject to change. Once you have the experiment completed and the model's done, then you're good. Then one more thing is that we can go in afterwards and we can actually confirm with, let's say, 6 blends, might be a good number. We can follow up this experiment, and at our ideal combination, we could actually go in and measure the different viscosities and turbidities. So, for example, if I'm just going to turn my attention to viscosities, we think that we're going to get a value, right on at the 43 level. But of course, results will vary, and maybe we'll get, some that are low and some that are high and some that are right on and so forth. But hopefully it would just vary, a little bit up and down, and we would end up with product that's within specification on average. And so in that case, it'll show you that here in the confirmation node. Now, if for some reason something happened to our detergent, some little bug got in there and started eating up, the viscosity of the solution, then, we would be in trouble, because pretty soon it's going to fall outside of the range. And so now it turns out we don't confirm. And I can make this a little bit bigger for you so you can see the bottom part here. So in this case, we're not confirming. So that gives you a quick run through. There's a lot more to it, but I think some of the highlights of what you would be doing with the program. Now let's move on to another example, which is good because it doesn't form a simplex. And this comes from Cornell's experiments with mixtures, example 4.5. And here he's showing a tropical beverage that's formulated from watermelon, orange, pineapple, and grapefruit. Now, the formulators don't want to put in 100% watermelon. I suppose it would be so weak and watery, even though it would be cheap. They realize that they can't do that. So when they set up this experiment, it formed a tetrahedral space, which is a simplex for 4 components or in 3 dimensions. And they cut the top off of it by forming this frustrum of a tetrahedron. Now Montgomery just kind of eyeballed this, and he put in the pure blends of the orange, and he got a sensory result of 5.8, the pineapple, and you can see the sensory results, and then the pure grapefruit. Then there are binary blends of these 3 juices, but up here is the highest or richest watermelon formulations, and he was careful to get that part of the space explored really well with 6 different formulations, which you can see the sensory ratings here. And it looks like we've got some that are pretty good here, above 7. So maybe in here someplace is a sweet spot. So what I'm going to do is demo something very similar, a fruit juice, but we've added a 5th component, and then we use the software tool for optimal custom design to try to locate the points, because if you try to do it manually like Cornell did, you'd start to go crazy with multi-dimensions. If you had 6 or more components, it would be impossible. So let me demo how this optimal custom design will work. So I'm going to go back to my tool, and then I'm going to open up a new file, which is called fruit juice. And I'll make it a little bit bigger. Okay, so now I want you to take a look at this And what I'll do to make it easier is I'll sort it descending. And so now you can look across and try to get some eyeball, or what Montgomery calls the interocular test, on maybe some conditions that give, pretty good taste. But also we're going to think about the cost, which we put in as an equation. So what do you think about that? Does that look pretty tasty or what? To make sure that you're seeing this output from Design Expert, press that raise hand. Okay, thank you. And bear with me, I'm a little bit paranoid about internet, so I hope you don't mind if I'm making you work a little bit to give me some feedback. So now we have a new case that I want to detail just a very quick bit in terms of how this gets set up. So this one actually gets set up here under the optimal custom, because if you try to do one of the simplex designs with this, it won't fit the simplex, and the program will warn you off of that. And actually, if you say yes, it'll just put you right back to the optimal custom. So we can't use one of the standard simplex designs for this because of the cutoff at the top on the watermelon. Now, the way the program works is it sets you up pretty much automagically with an optimal design, which is preferable for response surface methods and also mixture. If this was a screening type experiment for factorial, we would recommend the d-optimal design, which tends to put points more at the extremes. But the I-optimal is better for response surface. It puts points more in the middle. Now, as far as the search is concerned, we're going to go through a number of different exchanges. The old-fashioned approach is something called a point exchange that's based on the various geometric points. A newer technique is coordinate exchange that is more free to roam, but we do the best of both. And then in this case, we're going to try to fit a special cubic model, which is going to have a lot of terms for 5 components. In fact, it has 25 terms in it, which is shaded out. So we're going to give you at least 25 unique blends. But we also, if you don't change it, give you 5 unique check blends that are used for lack of fit testing. And then we furthermore replicate 5 of the first 30 of these to give you the pure error that are needed for the lack of fit test. So we've basically set up here all that you need, so that most times you might just accept these defaults. Just enter in your different responses. Again, we're going to look at cost. But right now, we're going to primarily look at flavor. And then it's working here, and boom, 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 with the fancier computers, the algorithms that take advantage of quad-core processing and things like that, we're able to get this design built very quickly, whereas back in the day, we would have to walk away and come back the next morning. Now it's done in a few seconds. So this would be our recipe sheet. We would mix up these blends and collect the flavor results from our taste panel. And of course, the cost is going to be computed. So I'm going to open up this fruit juice file again. So now we have the data. I'll look first at the cost equation in trace plot mode. And we can see that watermelon is very cheap. And orange juice is expensive. Pineapple juice is the most expensive. And grapefruit's kind of in between. So that's already fit. Now we turn our attention to the flavor. We designed this experiment to fit a special cubic. And in fact, special cubic is suggested, but also the linear model. In a case like this, what we do is we go with the higher order model, the special cubic, and then we reduce it. Because there's so many terms here, it becomes more advantageous to take out those that are insignificant. And I'm going to do this using the p-values, and then I'm going to take out the most insignificant term. It's going to refit, take the next most insignificant term, and it's going to go through a whole series of steps until we're willing to accept the results, adding in some terms to maintain model hierarchy, and this is our model here. And I'll make this bigger so you can see that they're mainly significant terms, except for a few terms that are needed for the higher order terms. This AC is supporting the ABC, and the BD is supporting the BDE term. No significant lack of fit, that's good. And then diagnostics at a glance. Don't look out of line for the normal plot, nothing outlying on the residual versus run. and nothing recommended for box, cocks, etc. So now we're ready to start tasting our juice. And this is a slice on A, B, and C, but it turns out that it's a little more interesting to look at the pineapple and the grapefruit. And the reason for that can be seen on the trace plot. The pineapple and the grapefruit have the most nonlinear impact, okay? So going back to my, let's go to the 3D surface. If I switch in pineapple and grapefruit and slice on the orange and the apple, then I can get a more interesting curvy space. And if I move the slice bar on the orange, I can look for higher results on the orange. Looks like right in there. And then with the pineapple, I can slice it. And it looks like this is pretty good right in here. So right in here are some formulations that we might discover where the taste is really good, above 8. Now we would get tired of looking at all these different dimensions pretty soon. So then we would, of course, naturally go to our numeric optimizer and just tell the computer to maximize the flavor. And we could just go for flavor without worrying about the cost. So just flavor alone. And we would get a formulation that's low on watermelon, high on apple, and kind of in between on orange, but low pineapple and grapefruit, and get 8.8 for the flavor. But if we also are worried about cost, because remember the manager is lurking, and that manager really wants to get the cost down. And if we made that really important because the manager doesn't care about the taste, only the cost, then we would end up with a different formulation that has less flavor, but it's much less in the cost per kilogram. So that's pretty much the story. How many of you would rather have a little more expensive fruit juice and get the better taste? Raise your hand if you like that. Okay, because I'm going to throw that out there because I'm thinking that most of you are probably more on the technical rather than the managerial side. So I think that's probably what we're going to do. And what I did when I did my beer blending experiment is I wanted to go for the best taste and to heck with the cost. So that's kind of my point of view. But of course, if we're going to start up a business, we better worry about cost as well. All right, I have one more case study with a little wrinkle on top of it. And this one, we're doing something really interesting. We're combining other types of factors with the mixture design. And these other factors can be numeric factors like time and temperature, or they can be categoric factors, and so forth. So one of the experiments that I've always thought would be fun would be to bake a cake out of differing ingredients and then use different time and temperature in 2 different ovens and then put some frosting on the top. So let me show you how that would work. So in this case, we're going to go to a custom design, and this is going to be optimal. And I'm going to put in, let's say, 4 ingredients of the cake, and let's say 3 ingredients of the frosting. I'm going to do time and temperature, which are 2 numeric factors, and I'm going to have 1 categoric factor, which is which oven. So in my hypothetical experiment, I'm going to make a pound cake that's going to be out of flour, butter, sugar, and eggs, and I would have to play with the total amounts and so forth, but just to suffice it to say these are the ingredients. Then for the frosting, I'm going to go with something artificial just to mix things up a little bit, and I'm going to put in some cream and some other type of filler, so maybe a fruit or something. And then I've got 2 continuous variables, which are the time in the oven and the temperature in the oven. And then the oven type is the last part. And this would be either an electric oven or gas. So that would be the mother of all experiments. And I won't press next because it would take so long to build it, and it would have so many runs that it would be impossible. But boy, you'd have a lot of interesting looking cakes and have probably a year's worth of tastings to go if you tried to do this experiment. Now, the experiment I'm going to show you is a little bit more manageable. The paint chemist, in this case, is going to try different mixes of the paint. But what they're concerned with is that when they switch from one monomer vendor to the other, that affects the hardness, the NOP hardness, and it also affects the solids content. And also they want to consider using one of 3 types of crosslinker for this, this little paint production. So let me open that file up. And this one is called autocoat. Let me back out of this big experiment on the cake and open up this other experiment, which is the autocoat. And here you can see, I'll expand the view a little bit. You can see the results here where they have varying compositions of the paint within the ranges that they established, which we can see here. And they have monomers switching back and forth between the 2 vendors, different crosslinkers, and then these are the results on the hardness and the solids. And what they want is they want at least 10 on the NOP hardness, which looks pretty good here, but they also are looking for above 50% for environmental reasons. So it looks like there's a few results here that might hit the spot. Can you see that? Press the raise hand button if you can see it. All right, good. Okay. And I have to apologize for the fact that I know maybe a couple have thrown some questions in, but again, because I've got such a large number of people and so much material to cover, I'm going to have to ask if you would, at the end, just email me any questions that you have jotted down along the way. And I'm hoping to hear from you, by the way, because that is very helpful to me to get that feedback. So moving on with this case study, let's just take a quick look at the results for the model fitting. It turns out there's a kind of a complicated way to contend with these what are called cross models between mixture Chaffee polynomials and more of the factorial type models for categorical. So it gets pretty crazy trying to fit these, but we have tools that will suggest models to you, which you can then do a selection method on. And in the end, in this case, we end up with a model that looks like this for the ANOVA, with these terms that are shown here being, relatively significant and no significant lack of fit. Nothing is abnormal according to the diagnostics. So now we can turn our attention to seeing whether we can get above 10 on the NOP hardness. And how is that affected by the monomer vendor? And it turns out if we switch to monomer vendor number 2, it's actually a lot better because we get this whole upper left, this red region working for the NOP hardness than we do for monomer 1. Now, as far as the crosslinkers are concerned, if we go off of the crosslinker 1 to crosslinker 2, it turns out that we don't get any hardnesses that meet our requirements. And we can see this in 3D surface a little bit better. So with crosslinker 2, we go too low on hardness. We need to have crosslinker 1, and better yet would be monomer vendor 2. Now, as far as a monomer and crosslinker combination, we can change our view to x, y coordinates like this, and now you can see how it's a combination of monomer vendor 2 and crosslinker 1 that stands above the rest. So these are 2 alternative views. Now with the solids, it turns out to be simpler because actually changing the vendors and changing the crosslinkers doesn't really make any difference to the solids content, is only a function of the ingredients of crosslinker, monomer, and resin. So for that response, it's just the 3 ingredients that matter. We can use whichever vendor or crosslinker we want. But to get those higher solids, we're going to have to be in this red zone at the top. Now these 2 responses conflict with each other. And so because of that, we're going to have to do a trade-off using desirability to both maximize hardness and the NOP hardness and the solids. And this ends up being the sweet spot with a certain amount of monomer crosslinker resin using the second vendor and the first crosslinker. And this can also be seen on the graphical overlay, trying to meet at least 10 on hardness and 50% on solids. And we can see here that if we switch the vendor to number 1, then it gets a lot worse. The sweet spot is a lot smaller, And if we switch off of crosslinker 1, then it closes off entirely. And of course, I would maybe consider we could use both the vendors with crosslinker 1, but I would also need to go back and confirm, whatever these results are by putting in some number of confirmation runs, let's say 6 confirmation runs. And maybe we would do a couple different locations, one for one monomer vendor and one for the other monomer vendor. So you can actually do multiple confirmation locations with this new version. Well, we have just a few minutes left, and I have one more little wrinkle. It turns out that to do this experiment, it's very tricky to have both monomer vendors at the same time. Well, because the salespeople for the 2 monomer vendor companies don't get along and they fight with each other. So we better separate them. And so we have a way of doing that using a technique called split plot. And this is a newer tool that came in with version 9. It was expanded in version 10. And so in version 11, you're going to have all the capability, and it's particularly of use for a combined design. So in this case, I'm going to rebuild the original experiment. And this time around, when I get to the entry of the vendor, I'm going to change it from easy to change to hard to change. And then we'll have to contend with that for our optimal custom design. I'm going to throw in 6 extra groups here so that I have plenty of changes from M1 to M2 to be able to get a statistical assessment of which one is better. So now it's going through an optimal build for the split plot, with the one being hard to change. And it's reminding us that we should switch or reset the process if we have one vendor after the other, which is just a random event. So in the first case, we have monomer 2 salesman coming in and bringing his stuff, and then we're making up various paints according to this recipe sheet with varying crosslinkers. And then we, of course, would measure the hardness and the solids. Now the second group is M1, so M2 leaves and M1 comes in. But then here where M1 is still a group together, we would have to start the process up again and do a reset. And then down below, you can see more of the M1s and M2s all the way down. So this is one more thing that can be done to make these experiments more practical and doable. You will pay the price on the hard to change factors, though. Those will not be assessed at the same significance level as the other inputs. So we'll keep that in mind. All right, well, we've reached the end of the hour-long session. I was hoping to accomplish a what's in it for you that would just give you an idea of what mixture design is all about on an introductory basis, to brief you on these tailored tools that hone in on optimal recipes, and then give you some real-world examples that show you how this can lead to that sweet spot, which is really where you're trying to get to, that meet all product specifications. So I hope you have seen how States makes formulation optimization easy for its users, and now you know. Raise your hand and don't be shy if I was too basic or too advanced. But those of you that felt like it hit a sweet spot with this presentation, press that raise hand button. All right, so I'm getting some affirmation here. And I appreciate the fact that this audience is very diverse. And some of you are quite advanced and some are just getting started. So all I can do is try to kind of hit in the middle of everything. We do present a class that goes through all of the ins and outs of mixture and combined design. It's a 3-day presentation that's called Mixture and Combined Designs for Optimal Formulations. And we do have a class coming up in November here in Minneapolis. And there's still, I think, some seats open for that. So if you have time and you have motivation, contact our workshop manager, Sherry, at this email address. Other than that, I would say, keep a lookout for the Formulation Simplified book coming out in 2018. That'll be available as ebook also. Well, I'd like to draw this to a conclusion and wish you the best of luck for experimenting. I thank you for listening, and then finish off with a quote, because I really am onto the data-driven type of discovery. And here Faraday is talking about how chemistry is necessarily an experimental science, not just first principles. Its conclusions are drawn from data, and its principles supported by evidence from facts. So I think that's a good saying to come away with. Again, thank you for listening. And as you leave, if you wouldn't mind just waving goodbye, I'd appreciate it. And by the way, as you're waving goodbye, make sure to make a note of this email address, mark@states.com, and get back to me with questions and comments, or even just attaboys. All right. So all feedback is appreciated. mark@states.com. Thanks again, and have a great afternoon and a great weekend coming up. Take care now. Bye-bye.